My name is Eric Peters. I am a project manager here with the Edge AI and Vision Alliance. I will be your track moderator today, your Q&A moderator. Our next talk is from Derek Chow and Shang-Hung Lin of Google and VeriSilicon, respectively. Derek is a software engineer for Google. He'll be up first. They're going to be tag teaming. And then Shang-Hung Lin is a vice president of NPO technology with VeriSilicon. He has 25 years of experience. They're going to give you a wonderful presentation on something very exciting to me, which is the concept of distributed neural cascades and how we can break some of that really heavy compute across devices. So please help me welcome, first up, Derek Chow.
Thanks, Eric. Hey, I'm Derek. I'm here with Shang-Hung here today to talk to you about image tokenizations for distributed neural cascades. So just to make sure we're all on the same page, let's start with a little bit of a definition of what tokenization is. So we'll define tokenization as the process of taking some form of sensor modality and converting it into a neural representation. That's a lot of fancy words, so maybe breaking things down into a couple examples might be a little more illustrative. So here are two examples of variational autoencoder type networks. On the left, this is a variational autoencoder for an MNIST network, but we can sort of generalize this concept to sort of any image network, where we'll apply some form of CNN that will take the 784 scalars used in an MNIST image and then compress that down into a smaller size latent vector. So this could be some smaller number, let's say 32 different scalars, through an encoder network. We could then take this latent network, or this latent vector, and apply it through a sort of a matching decoder network. And feeding it through this decoder network should, ideally, give us our reconstructed input. So this is some way of building like a neural compressing algorithm for images. On the right side, just to show that this sort of generalizes beyond images, is a similar concept applied to audio. This is the soundstream network used in the Lyra V2 codec. So it's a very similar idea. There's a CNN that takes frames of audio and emits another set of smaller frames, but of lower cardinality, applying some form of compression. In the case of soundstream, they also use a concept called residual vector quantization, which allows us to sort of compress things into an even smaller number of bits, really getting us some form of data compression. So why are tokenizers really useful? And so there's two really nice properties that we will leverage from tokenizers for this talk here.